Advanced Cooling Technologies, a global leader in delivering thermal management solutions for military, aerospace, and commercial markets, presents its latest in a series of instructional videos on advanced thermal technologies. You'll learn the basic concepts of pumped two-phase cooling, also known as evaporative cooling or flow boiling, and identify the benefits of the technology, which have attracted the attention of so many thermal engineers. You will also discover how the technology works and how stable it can be, even in an unstable multi-evaporator environment. Most engineers are familiar with pumped single-phase cooling. It's used in car radiators and as cold plates to cool electronics. In these systems, a fluid, such as water, ethylene glycol, or a refrigerant is circulated from a pump through a cold plate where it removes the waste heat from the device. The working fluid, now at an elevated temperature, goes to a heat exchanger where the waste heat is dissipated. The working fluid then goes to a reservoir tank where it is ready for the next cycle. These systems work well in many applications, but increasing heat loads demand higher liquid flow rates, which result in larger pumps and more power. Also, as the liquid traverses through the cold plate channels, it increases in temperature. In some cases, the increase in temperature, delta T, from the inlet to the outlet can be significant. Pumped two-phase or evaporative cooling systems use the same basic system-level components as the pumped single-phase system. However, pumped two-phase systems typically use refrigerants as the working fluid. Through refrigerant selection and appropriate controls, the refrigerant is designed to boil as it acquires heat from the hot surface of the device. More heat can be removed through the boiling process, otherwise known as latent heat, than through sensible heat with single-phase cooling. Boiling across the entire evaporator surface offers a further advantage in that the evaporator will have a very uniform surface temperature, typically within a few degrees. This near isothermal performance is important for many applications, such as laser devices, which have wavelength emission sensitivity. Another key advantage of pumped two-phase or evaporative systems is they do not require high coolant flow rates. As a result, smaller pumps requiring less power and weight can be used to remove higher amounts of heat, in effect, increasing the coefficient of performance, or COP, of the cooling system. This means more heat can be removed over a given surface with less pumping power. This is important for applications that must be compact and operate with minimal power. In terms of weight and power savings, we've shown that for an 80 kilowatt heat load, a pumped liquid system would require a pump that utilizes 5.3 kilowatts of power and a flow rate of 134 liters per minute to remove the waste heat. By contrast, a pumped two-phase system would require pumping power of only 250 watts with a flow rate of 25 liters per minute, plus an 80% reduction in flow rate and a 95% reduction in power. At Advanced Cooling Technologies, we've been working on pumped two-phase cooling systems for more than 10 years. We develop standalone, completely self-contained cooling systems for several high-power electronic applications. One of the common requirements of these applications is that the cooling system must provide coolant from a single source to several evaporators simultaneously, with each having a different heat load. Here we see 4 parallel evaporators, each identified with a specific color, and each with the capability of dissipating different heat loads. Evaporator 1 is red, 2 is yellow, 3 is orange, and 4 is blue. Here is a sample of one of the evaporators. The hot device is attached on one side, and the fins, which is viewable in the demo unit, is on the other. Under steady-state conditions of applying 300 watts to each evaporator at a heat flux of 80 watts per centimeter squared, we can see the incoming liquid begin to boil as it moves across the hot evaporator. At the end of the evaporator, we see mostly vapor, removing the waste heat. You can see the temperature of the evaporator is constant. Additionally, the fluid flow seen both on the graph and the display also shows steady performance. Now we begin to cycle the heat load on evaporator number 2. The heater is turned on for 2 seconds and off for 5, simulating a variable heat load. You can observe that flow boiling at evaporator 2 becomes staggered and erratic as the temperature drops below the boiling point of the refrigerant. However, the performance of the other 3 evaporators remains stable. We will now begin to cycle the heat load on evaporator 4 in a similar way as evaporator 2. Again, we see erratic boiling at both 2 and 4, but flow rate, temperature, and boiling remain constant for 1 and 3. Now we stop cycling the heat loads and see that all 4 evaporators are stable with constant heat load. A key feature that enables this flexibility was achieved by placing flow restrictors in front of the evaporators. we can ensure that each of the evaporators receives the appropriate amount of coolant. This allows the performance of the other evaporators to remain unchanged as heat is applied to different evaporators at different times. In this way, we ensure that each evaporator provides adequate cooling to the device as the other devices turn on and off. Not only can pump two-phase cooling operate in an unstable, multi-evaporator environment, you've learned pump two-phase cooling can handle higher heat loads and is more efficient than pump single-phase cooling. If you'd like more information on pump two-phase cooling or any of our thermal technologies, please call us or visit our website at one-act.com.